Welcome back. Section 4 already. Well, the last one was pretty short, so I know you're excited about moving on and getting a little bit more information about what you can learn in statistics. So this time we're going to talk about the normal distribution. In other words, when you have a whole bunch of data, sometimes it has a normal dispersion or distribution. If you graph it, it has a nice curve, which we'll see. And there are a lot of nice characteristics about it too. So without any further ado, let's get rolling on this. So what are we going to do? First of all, we want to see what normal distributions look like when we graph them. We want to talk about the 68, 95, 99.7 rule. We want to find scores at specific standard deviations from the mean. Scores are sort of like the original data, except special maybe. We're going to use the 68, 95, 99.7 rule. We'll convert a data item to a z-score. This can be very handy. Just looking at a z-score can tell us a few things. You'll find out. Next, how about percentiles and quartiles? Maybe you're familiar with percentiles, but not quartiles. Well, if you know percentiles, quartiles are very similar. Instead of breaking things up into hundreds or hundredths, we're breaking them up into fourths. That's all it means. And next, we'll talk about margins of error. Last of all, take a look at some distributions that are not normal. How can you tell if something's normal if you don't know what's not normal too? You have to be able to tell what the difference is between the two. So, let's get started with normal distribution. It's also called the bell curve. You've heard of that. And you probably haven't heard it called the Gaussian distribution unless you've taken some statistics in the past. Notice it's bell-shaped. That's why you call it the bell curve occasionally. It's also symmetric about a vertical line through the center. In other words, it has a middle, and the right and left side are mirror images of each other. Keep that in mind. This is very interesting. Remember the mean, median, and mode? Well, if it's a normal distribution, then the mean, median, and the mode are all at the same place, right in the middle. Here's a picture of a normally distributed one. Now, it's not a perfectly normal distribution, but nothing's likely to be perfect. That's one example, and this is a random sample of 100 then. This is a sample of more, and every time you increase the size of the sample, if it's a normal distribution, it looks a little bit more smooth. The right and left side match up just a little more carefully. And there's a bigger sample size, a lot bigger, and see the two sides look like they match, except they've gone through the mirror, they've gone through the hourglass, so to speak. And there's one with, you might say, almost an infinite number of data. And it really looks smooth. If you took an electron microscope and looked very carefully here, you might see some rough edges, but not like you did back here and here and here. Normal distribution. Now, here's a picture, and there's something you ought to know from this. The shape depends on the mean, which is right here. It's that middle part. And the standard deviation. Standard deviation means how widespread is it. So the whole shape of the normal distribution depends on just those two characteristics. The mean, the average, and the standard deviation, how widespread it is. Three graphs coming up have the same mean but different standard deviations. Oops, it's already here. If you look at these three curves, and I'm not perfectly sure what colors you see. Let's say this one's black. I'm not sure what you see exactly. This one, the middle of it, notice, is right here. Middle for the blue, the distribution is right here. And for the green distribution, the mean is in exactly the same place. But they have different standard deviations. Imagine you took this green one, grabbed both sides, and pulled it to the left and to the right. You might end up with the blue one. If you pull it a little bit further, you'll end up with the black one. That's sort of an idea. The dispersion is how spread out it is. When the standard deviation increases, your curve gets more spread out. Now we get to the 68, 95, 99.7 rule. What that means is, here's your curve. It's green in this case, or blue, whatever. Here's the mean right in the middle. And if we go one standard deviation both ways, all this data in here makes up 68% of all the information. If you go one standard deviation both ways, this part right here makes up 95% of all the data, all the people, or all the 2x4s, or whatever it is that you're measuring. If you go out 3 standard deviations both ways, then you've seen just about everything. 99.7% of all the people or things are within 3 standard deviations. 68 within 1, so 68%, 1 standard deviation. 95, 2 standard deviations. 99.7 within 3 standard deviations. Remember, that's going in both directions at the same time, covering more area, sort of like you're painting in. How about scores at specific points? Well, let's take a look at an example. Male adult lengths in North America, if they're normally distributed, and they are really, they have a mean of 70 inches. Remember, we're talking about heights, so it's in inches, and the standard deviation of 4 inches. Now, what I do when I'm working one of these problems is, I don't want to have to read this whole paragraph over and over. So the first thing I do is say, okay, it says the mean of 70, so I write it over here. Mean is 70 inches. There we go. And the standard deviation is 4 inches. Maybe put that in a box. Maybe put some color to it. That way I can find this information anytime I need it. I don't have to go read through the paragraph again. Now this one says, find the height that's 2 standard deviations above the mean. Well, the next thing I do is, and I'm not an artist, as you can see, but I create a picture. Here's my normal curve. It doesn't look very normal, but the picture just is going to lead me and help me find a way. So it says 2 standard deviations above the mean. So if I go 1 standard deviation here, and then another standard deviation here, this is the point I'm interested in. Now, how big is that standard deviation? Well, look over here. This place right in the middle is the mean, where you find the mean, median, and mode. And this standard deviation is 4 inches away. So if I go this far, I'm going to get to 74. But this is 2 standard deviations away. So I need to go another jump, and that'll take me to 74 plus 4 more is 78 inches. And there's our answer. That is the height that's 2 standard deviations above the mean. Easy as that. Now, what I'm going to do is I'm going to clear that so you can see what's coming up here. Okay, so the solution. Well, this is like an instant replay. There's your height you're looking for. Start at the mean. And 2 standard deviations. What are the standard deviations? Each one is 4 inches. And this is 70. And a little bit of calculation. And there's our final answer. Almost. Except don't forget the inches, right? You know better than that. Now we're going to use the 68, 95, 99, 4, and 7 rule. First of all, we've got a distribution of those male adult heights, and we're going to use that to find the percentage that are between 66 and 74. So what do? We start right in the middle. Start in the middle because that's the mean. Now we're interested in 68 to 74, so if I go this direction, 1 standard deviation, oh, that's what I'm interested in. Big check mark there. If I go the other direction, for below 70 is 66, that's the other one I'm interested in. Now, what percentage is between those two? Well, those are each 1 standard deviation away to the right and 1 standard deviation to the left. And by our 68, 95, 99.7 rule, from here to here should be 68% of the data, or in this case, 68% of the men are between those 2 inches. Those 2 lower bound and higher bound. And you might think about that. So remember, this one, the 66 inches, is 5 foot 6 inches, and this is 6 foot 2 inches. Now, doesn't it make sense that these 2 would cover 68% of all men in North America, adults that is. That's how you work it. They're both within 1 standard deviation for the 68 or 66 and the 74. Mean minus 1 standard deviation, mean plus 1 standard deviation. And there you get your 68%. Next, z-score. Well, this gives me a lot of z-fun, because if you want to pretend you have a German accent perhaps, and don't give me any German nonsense. Part of my heritage is German, so I'm not making any jokes about Germans. How do you compute z-scores? Well, it's very easy. It's going to talk about how many standard deviations. So if you connect standard deviations with z's, you'll be in business. The z-score can be obtained by just such a calculation. The data item, usually we represent a data item by an x. And the mean we usually represent by mu for our population, if it's the mean of the population. And on the bottom, standard deviation. And there you go. Do the subtraction on the top, divide by the bottom, you've got your z-score. A good thing to keep in mind that data items above the mean have positive z-scores. Data items below the mean have negative z-scores. So if you go back to a picture again, this is where you have a z of 0 because it's not above or below the mean. Items over here have positive z-scores because it's above the mean. Data items over here are below the mean, so they have negative z-scores. Put the picture and the concept together. Remember also that not only the data items above are positive z-scores, below are negative, and the z-score in the middle is exactly 0. Now let's see if we can do something a little bit more constructive with our time here. We've got a mean weight of newborn infants is 7 pounds. So what I'm going to do right away is mean is 7 pounds. So I'm going to write this in a box. And it says the standard deviation is 8/10 of a pound. So the standard deviation equals 0.8 pounds. And I've got it. Anytime I want those two pieces, I don't have to reread this paragraph. I can just go right to my box. Now it says the weights are normally distributed. That means we know a lot about them already. You want to find the z-score for a weight of 9 pounds. Well, first of all, that's above 7 pounds, so it's going to have a positive z-score. A positive. Now, how do we calculate it? Let's sneak back here a second. This is how you calculate it. I prefer to remember this one. So, if I want the z-score, I take the data item, that's 9 pounds, subtract the mean. Where's the mean? Well, I've got it in the box. 9 minus 7. And on the bottom, standard deviation, where is it? It's right here in the box. 0.8. And a little bit of calculation, very little, and you've got your z-score. There's at 9.7 and the 0.8. A little bit of simplification and maybe some calculator work, or maybe you can do it in your head. That's even better. So the z-score for a 9, that's what this means, a z-score for a value of 9 in this situation is 2.5. 2.5. Notice another thing too, z-scores do not have any units, because if you look at these items on the top of the fraction, both of those are in inches. Subtract inches from inches, you get so many inches. On the bottom, standard deviations are also in inches, which means you're going to be dividing inches by inches. The inches cancel out just like anything else. 2.5 is it. No units. Z-scores do not have units. Let's take a look at another one. IQs are normally distributed, like a lot of things are. Not everything, but a lot of things. Has a mean of 100. You know what I'm going to do. There's the mean, the standard deviation. 16. Now we want to find out what IQ has a z-score of negative 1.5. Well, let's go back to the formula. Z equals x for the data item minus the mean divided by the standard deviation. Okay, what does that mean? Well, the z-score in this case is negative 1.5 equals the x-score, we don't know. We're going to find that. The mu, right up here, 100. Standard deviation, right up here, 16. All I have to do is solve this simple equation. That's why we did chapters 6 and 7, so we could do a little bit of algebra when we needed to. Now, notice that we've got a fraction on the right-hand side. The easy way of clearing fractions is multiply by the least common denominator. The only denominator is 16, so we'll multiply both sides by 16. So 16 times negative 1.6 on the left side, and 16 times x minus 100 over 16. These 16s will cancel. You'll have negative 9.6 equals x minus 100. Add 100 to both sides. And x, oops, that wasn't supposed to be negative. Yes, it is. Negative 9.6. So add these two together and you'll have 91.4. Now, before we leave this slide, take a note of something. Right up here where it said the z-score was negative 1.5, that negative means it's below the average. It's below the mean. So we should be talking about something that's less than 100. And sure enough, there's our 91.4, which is less than 100, the mean. Let's clear that so it doesn't look so cluttered as we move on here. Clear that, come on. There we go. Erase the ink. All right. So just a little bit of a review. The negative sign in negative 1.5 says the IQ is 1.5 standard deviations below the mean because of the negative. Oops, I guess I made a mistake, didn't I? My apologies. 76 is the actual standard deviation. So you can go back and fix that in your notes if you didn't already fix it. Okay, now percentiles and quartiles. Keep in mind here, the percentiles means, say you have a set of data, and suppose this is the lower part of the data, this is the higher part of the data. Percentiles means we're going to take all this data and we're going to chop it into 100 little pieces. And each of these pieces will be a percentile. So right in the middle here is the 50th percentile. Why? Because 50% of the data is lower than that. Get that? The percentile, that's what percent of the data are lower than that particular item. The connection of the quartile is like this, and you can see it really well in this picture. Quartiles means we've got quarters or 1/4. So you've got set 25% of the data here, 25% here, here, and here. It's chopped it into 4 pieces instead of the 100 pieces we had with the percentiles. Notice that the 3 important quartiles are the first quartile, which is the same thing as the 25th percentile. The second quartile, also known as the median, is the same thing as the 50th percentile. It's right in the middle. And the third quartile is the same as the 75th percentile. Hopefully you've caught on to that real quickly. If not, back up a little bit, think about it, listen to it again. So how about an interpretation for those z-scores? With a z-score in a calculator, you can find the percentage of data items that are less than any data item in a normal distribution. Keep in mind, we are talking about normal distributions in this section. In a normal distribution, remember, the z-score is right in the middle, where the mean, median, and mode have met. It's the 50th percentile, right in the middle. Z-score is 0. Mean, median, mode, 50th percentile. All of them are exactly the same place. Now, this is what you hear, especially during election times, margins of error. And here is a margin of error that's sort of a quick one. This is for the 95th probability. If you talk about the 95th probability, we're trying to be correct 95% of the time. This will give you your margin of error. What does this mean? Well, it's plus or minus a certain amount. 1, of course, is 1. This n that's in the square root is the number of data items, or the number in your poll. Convert that to 100%, and you know that whatever score you get will be plus or minus this percentage that you get from this. So here's a small example for you. We've got a random sample of 1172 children, ages 6 to 14. 17% said getting bossed around is a bad thing. One of the bad things about being a kid. What's the margin of error? Well, the sample size is 1172, so we'll just take this simple version because we want to be 95% correct, or excuse me, we want to be correct at least 95% of the time. So we put the 1172 in for n and take the square root of it, divide into 1, convert that to a percent, and we're sure of that answer with a plus or minus of 2.9%. So the 17% is correct, plus or minus 2.9%. So if you take that 17 and subtract the 2.9, then we'll have 1,541. So the real number is between 14.1 and, let's do this again, 17% plus the 2.9%, and that gives you 19.9%. And our real number, now we're telling people that 17% of those children say this, and that's sort of accurate, but you should have a range. And this is how you get the range with the margin of error. Take this number and with the 95%, use this, subtract it from the number you got. That gives you the low value, and there's the higher value. That means you're 95% sure that the 17% is really 14.1 to 19.9%. 95% sure. There's almost no chance that it's exactly 17% because you took a sample. So you don't know that that's the case for the population. But you know that the real value for the population should be between 14.1% and 19.9%. And you're 95% sure of that. So how would your statement go? How do you write this up? And that's one of the important things that you need to learn about when you take statistics or read statistics. First of all, remember what we just did. There's 95% probability that the true population lies between 17 minus 2.9%, that's the 14.1 we got, and 17 plus 2.9%, 19.9%. And that's how you would describe it. Now, let's wrap this up with some other types of distributions. Not all distributions are normal. Remember, the normal one is this nice bell curve. That didn't turn out too badly. Some distributions don't look like that. In fact, in this case, there are a lot of data values to the right. In other words, the tail is to the right. Another way of saying that is it's skewed to the right. The direction of the tail tells you how it's skewed. Now, since it's skewed to the right, that also means that it's positively skewed because to the right. So you might want to write those things down for you. This one is not normal. It's pulled to the right, the tail is on the right, so it's skewed to the right or it's positively skewed. And that gives you an idea of where the mean, median, and mode are. Because you've got a lot of values, here's the mean. Because you've got a lot of values back here to the left, it pulls the mode to the left and it pulls the median to the left. And they're always in this order. The mean is sort of the starting point. If you're moving away from it and the three aren't in a normal distribution, the next one you run into is the median, and furthest away is the mode. Well, folks, that does it for the normal distribution. And if you need to find any of those values a little bit faster, we can do those with the calculator. Remember, bring that to class. And also keep in mind the one thing I didn't bring up here is this, but I did mention it. It's a skewed distribution. In this case, it's skewed to the right or positively skewed. If it's pulled to the left, it's skewed to the left, and it's a negative skew. Well, that's it for section 4. Only 2 to go, and we're getting pretty close to the final exam. Keep your eyes open for the review coming. We're going to have the final exam and chapter 12 at the same time. That gives us sufficient time to review before the final exam. So the final exam will be skewed toward chapter 12, but with a sprinkling of things from the rest of the semester. Well, you take care of yourself, study hard, and I'll see you soon. Bye.